Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. And this video today is basically the final week of assembly language. We're dealing with advanced functions, so we're dealing with pushes and pops onto the runtime stack, and we're including everybody's favorite word, recursion. And so we're going to do a recursive function. This is your activity that I'm going to look over here for week 16. And so here is the problem. I gave this to you in C++. And so what am I looking at here? All I'm doing is calling the function. There's prints inside of here, so there's no need to print anything else outside of this function. And then an end line, a system pause, and a return. But what am I doing in here? This is my out, hopefully, right? That's the whole point of recursion, is you have some base case that finally absolves you of calling the function over and over and over and over again. Eventually, you're supposed to get yourself out of it so that you can unwind all of the calculations you've been doing, and in the process of the unwinding, end up with the solution to your problem. So you're taking a problem like, well, what is the recursive function of 109? And then you're breaking it down to, well, and you go like, I don't know, but I do know that it's this, if I print out a value, then I can call it on a smaller number. And so let's say, what is this mumbling and rambling all about? The point is, a recursive function takes a problem that you do not know how to solve and reduces it down into a simpler problem, and that, basically one or two or more simpler problems that maybe you can't even solve those, but eventually all those simpler problems can be solved. And then that one problem reduces down into a whole series of solvable problems, and you basically sum up everything that you get from all of the simpler solutions. And that's what we're going for here. So if my x value, which starts out at 109, if it's greater than 0, go in here and do something. But if it isn't, if it's less than or equal to 0, then we're done. And we can kick out of here, and basically, since the recursive function ends because we're not calling anything if we go through and hit this closing curly brace to come back, so everything should start to unwind. So as long as the value is non-negative and positive, which this thing does, what do I do here? And this is the even odd check, right? I mean, we're probably still used to seeing if x mod 2 equals 0 or something like that. But again, bitwise and takes one clock cycle as opposed to a division that takes many, many clock cycles to get me to the same place. So we're going to use a bitwise and operation. So this just says if x is an even number, subtract one off, so makes it an odd number, and call the function and then print out the x. So this is an immediate thing, right? The pre-decrement here. So basically, I'm turning a even number into an odd number and then calling recursively. So when I come out, I'm going to print an odd number. And if this is false and this is an odd number, I'm going to print the number out. So I never should see an even number being printed out. So let me see what happens when I run this. I have 109, I got 53, 20, well, blah, blah, blah. But what happens, let's see, let's just make this 1110. And what do we get? Just to throw something out here. And you can see here that even if it's 1110, it's basically odd numbers all the way down. And so the recursion makes everything fun, makes everything interesting. What about 110 and so forth and so on? But what do I get? And it's interesting, right? Because you're getting values that you're not thinking you might get at the end. 109, 53, 25, 11, 3, 3, and then you're getting a 109. And that's because if I'm starting out with an even number, I'm calling everything. I'm decrementing the 110 to 109, and I'm doing all the recursiveness. But when I come back at the end of the day, I'm still printing out x, which is the 109. Even though I've reduced everything down to this, I'm still printing one more. That's why this came back like, why is that? Why is he printing when it's 1110? Why is it printing all these extra numbers after after a 1 or a 3 or something? And again, it's because of when the recursion returns, I'm still printing out a value, which was something before I called the recursive function. So let's see, all that for 1110. What happens at 1111? There we go. And it's still the same kind of deal because there are because as I'm reducing, there are even numbers. You never see them, but even numbers get me in here to turn them into odd numbers, and I still print numbers after I return back from things. So it's a pretty interesting sequence and series. I just made this off the top of my head one day for you guys to do. Okay, so we're going to solve this problem. This is, of course, C++. And so the first thing I want to do, as is my way of doing things, especially when I have a function written out like this, is I'm going to turn my parameter here, which is my parameter, and I'm going to turn it into a -8. No, +8, sorry. It's too easy to get confused, right? So remember, the first parameter that gets thrown onto the stack after you do all this cool stuff of getting everything ready, push and put a thing on the stack and all the other stuff, is that my first parameter becomes EBP +8. So anywhere I see this X, I'm going to replace it. And it should be pretty easy to do because I don't have anything else going on for me here. And then I don't have any, at least at the moment, maybe because this is going to be a temporary variable or temporary value coming out of this, is that maybe I will need something else. But for the moment here, I don't need any local variables. And let me run this just to make sure I'm on the up and up here. Yep, okay, I'm right back where I was. Good, good, good. And so I have everything I need to go forward. And so now my X is going to be EBP +8, D-word EBP +8 or something like that, just so you can get a feeling for what's happening here. And so let's begin. Okay, so I'm going to do the main first since that's pretty simple. And so what I'm going to do, that 11 and 11, 11 is going to be pushed onto the stack. And then I can call my function. I'll just call it recurse. I'll just call it R. Yeah, I'll just call it R. Make it easy on myself because I'm going to spell it wrong. And so that's all you do in this, like with this new chapter 8 quote-unquote style way of doing things. Whenever I have a parameter to a function, I'm going to push them all onto this, one or more, I'm going to push them all onto the stack and then call the function. And so remember, I'm pushing a value on the stack, and when I hit call, I'm actually putting another value on the stack, which is, of course, the return value when the function ends, this R function when it returns. And so, but right now it would be like whatever the memory address of the start of line 12. And so that's where you get the +8 from, because I'm putting the 1111 on the stack, which is 4 bytes. I'm putting the memory address of this guy on the stack, which is another 4 bytes. And so when I do all the work, I get EBP +8 when it comes to, when it comes to where in the stack is this 1111 located. And so, and local variables, as you remember, would be subtracted off, but again, we're not doing that. So that's all we need to get that going. And then I can do a call CRLF. I can do a call wait message, and I just exit. The return 0 is unnecessary here in C++ land, or I'm sorry, in assembly language land. That's already part of the exit here. And so that is it for main. And to make this thing work, at least for the moment, I'll have to have an R, and I'll have to see if R is even a keyword or something like that. rproc. Let's put a ret for the moment, R and P. Okay, and let's see, will this run and just give me nothing? Yep, and it does. So I'm very happy with that at the moment. And so the main is done, and I have a basic skeleton outline for my R procedure, and now we're ready to kind of go in and do the nitty-gritty details. The nice part about this is, since we know we have working C++ code, or just working code in some language that's simple, that it should just be a matter of translating line for line for line. And people freak out. I always freak out about recursion, depending on the problem. Like even like have you ever done the Tower of Hanoi problem? And like to this day, it's only three or four lines of code in C++ or Java or you name the language, but like I have it memorized. I know what it does, but it's like just the thought process of recursion of what it's actually doing. Like I get that it's changing things up and changing things up, but it just feels like magic that those 4 lines of code, if I just let it run to completion, no matter how many disks, will always work out for us. It's just an amazing thing. So, and the same thing goes here. For sometimes you just throw up your hands and say it works, but we absolutely need recursion for things like sets and maps and anything that basically binary trees. We absolutely need that recursion to save us tons and tons of code on the back end. Because if you've ever seen like the Tower of Hanoi again, it's 3 or 4 lines of code in recursive code, but it's tons of code in iterative code that does not call, a function that does not call itself over and over and over again, that uses loops and other things, it complicates the matter so very much if you do not use recursion at all. And so we're ready to move forward again after a couple more minutes of talking this problem out. Let's get to it. Okay, so the first rule, of course, is if I have any parameter passing, or, this is not an XOR, it's an or local variables, then I need to go ahead and set up the EBP register. So I do the push, I push EBP, I move ESP into EBP. I have to make sure I write this all out right while I'm talking. And then on the back end, I push EBP back. So that handles the EBP register, and later on we'll fix up anything else. I don't even, we don't know yet. Am I gonna blow out anything? Because this is a void function, and so if I change any register at all in here, I got to put it back. And so, but again, EBP is done. But now this ret, remember, this is where you get to clean up any of the things that were pushed on the stack here for parameters. So remember, the rule of thumb is 4 times the number of parameters passed. So I'm going to ret 4 here. And at the moment, I don't have any, like we were talking, I don't have any local variables. So I don't need to add a subtract up here and an add down here. And so at the moment, we are good to go. All of the setup for parameters and local variables are done. And now I can go ahead and work on the main part here and start getting into the actual if statement. Like, when is Brad going to get to the meat of this, right? He keeps talking and talking. But you really do have to set all of this up ahead of time, because, I mean, that's just the way things are done. Okay, so this if statement. If I plus 8 is greater than 0. So some kind of comparison. And so, let's see. I'll use the label end now. I'll just call that here. So here is my comparison. Compare the D word pointer of whatever is at EBP plus 8. Compare that to 0. And again, remember, every video I say this, whenever you have like an if statement, you're like, well, what do I have to, in high-level language, you go, well, what do I have to do the code? But when you're working in assembly language, you're really thinking, how do I hit this end condition? How do I get out instead of how do I get in? And so you just flip the sign inside out, and you go, well, this is going to be a jump if less than or equal, because that's the opposite of greater than, and I'm going to jump to end now. This is not a loop. Other times we're like, oh, put an again up here, label, and then jump down. Nope, this is just an if statement. So so the only difference again between an if statement and a while loop is what you see here is if statement is done, but a repeated if statement as a while loop means that I would put a second label up here where the cursor is blinking, and then I'd put an unconditional jump down here. So that's the only true difference, because an if statement is run one time, and a while loop is run as many times as needed until the end condition is met. So recursion in a way is just a different way of just doing the same thing over and over and over again until an end condition is met. It's just you can blow out your call stack, you can get a stack overflow, and you can get all sorts of crazy stuff if you're not 100% paying attention to what you're doing. Okay, so if statement is complete, at least the first if statement. And so I can go ahead here, oh, not that one, this one here. And now we're ready to go ahead and look at the second one. You just put the comment here on the side. Oops, that's not. Put that here. And I can move this over a little bit so we can see what's going on more, since this is all we need here. Okay, good. So I can have this a couple more times. All right. So now let's look at the second if statement here. So what I'm going to do here is I'm going to use my test operation. I don't notice that this isn't changing. This is creating a temporary. I'm not changing whatever's at plus 8. I'm just taking plus 8 and I'm doing a bitwise AND on it, and then I'm comparing it to 0. So plus 8 is not being modified, so there's no reason for me to go ahead and do anything that's destructive to either plus 8 or any of my registers. So I can go ahead down, you gotta make sure I put it in the right place here, like right here. This is where I can say, hey, let's test my D word pointer at EBP plus 8. And let's go ahead and compare that, or let's test that with 1. So this goes before, and now what this does is, it does the bitwise AND. Remember back to your notes, test is just a non-destructive AND, just like comparison, CMP, is a non-destructive subtraction. it's actually, you know, comparison is just a subtraction that doesn't modify any of its operands. A test is just an AND operation that does not modify any of its operands. And so now what I'm going to do here is this test, all this is going to either set or clear the 0 flag. Because inside of here, when this comes out, this is either going to be a 0 or a 1, because this is a bitwise AND operation with the least significant bit of whatever plus 8 is. And so what I can do here is, you know, coming back to this, well, okay, what do I want to do if I'll say is 0, and then I'll have an is 1, because I want two labels here just to show you what's going on. Because based on the result of this test, I need to either go do this code or I need to do this code. And so, you know, what am I going to do? And it really doesn't matter how you work things out. But again, in this case, I'm just going to keep consistent and say, well, how do I make this thing false? So if jump, if not 0, to is 1. Wouldn't that be correct? Because if this isn't true, you know, then this value has to become a 1. Because again, it can only be a 0 or a 1. And this is only false if this is a 1. This calculates out to a 1 to come down here. And so test against 1. And if I get a 0, then I go, nope, it's an even number. But if it comes through here and I go, okay, I get a 1 out of this, it's a non-zero value, it has to be a 1, and I'll come down here. And now you could technically get rid of this label, but labels are there to help you. They're almost, you know, like they're not always there just as, you know, ways to get back and jump to places. This can be considered a comment, even though you're not technically commenting anything, because you're like, oh, okay, this is 0. Let me do the code. Let me do whatever this is here, and then I can move on and do other things. This is 1. Oh, hey, that's what happens is, if, you know, or if you want to say is true or is false, whatever gets you to, you know, to do the stuff that you need to do. I'm famous for never being able to come up with the best names for variables and functions and whatnot. That's just my thing. I'm not famous for it. I'm famous in my own head for it, of course. Okay, so now we're ready to go, and now we're just ready to finish up and do the work. The end now is perfectly fine. It's still great because this will come around everything, right? If I jump from here, this is my initial if statement. I come all around all of it, and then I return back and I pop. So, okay, so we're ready to continue forward now. All we have left to do is either this inside of the is true or this inside of the is false. And then I cross my fingers, run my program, and go, did I do it right? And we'll see if I did it right. Because at this point, I might have made a mistake already because I'm talking, thinking, doing, a trifecta of causing errors and bugs in my programming. But we'll get there when we get there. So let's see, I want to call this guy here. I want to do this work. And so I want to call this parameter, but I want to do, the decrement is an immediate operation here. So what I can do here is I can just call dec, and I can say dec on d word pointer EBP plus, EBP plus 8. All right, I can dec, and that's where I do need the d word pointer here. I can rebuild, and you can see, oops, I have an error somewhere. Uh-oh, where do I have an error? I'll run this again. Let's see what's happening. Nope, it succeeded. I don't know what the... Oh, that's weird. I thought it said something went wrong. But you can see rebuild all succeeded down here at the bottom. But if I get rid of d word pointer and I run this again, I get an error, and it does say all failed there. It did say that. And you go blah blah blah. There is 2 errors and 1 instruction operand must have size. It doesn't say correct size. It just says size. Remember back that EBP is just a pointer. It's just a memory location. And even if I do an offset on it, I'm getting a memory location out of the deal. But this means, hey, subtract off. But do I subtract it off as a byte, a word, a double word, who knows, like a point, like a object? What do I do? And so that's why I need to include this to tell the assembler, hey, I know this is a pointer. Treat this address like a double word, because I know that's what's sitting on my stack, and now we can decrement that. All right, so I decrement, then I can push the word. I should probably take this and keep it copied so I don't have to type it every time. I'm going to push that value onto the stack because now the decremented value is my parameter, and I will call this function, call R. All right, that's how I turn this line of code in C++ into 3 lines of code here in assembly language. And so now when I come back, what I want to do here is this print statement. This is going to be a couple lines of code in itself. So what do I do when I get back from this guy? I move into the EAX register, my D word pointer at EBB plus 8, because the write int function, or in this case the write dec function, that will print out an unsigned value. I don't want to, I don't need to print that plus every time. So I'm just going to print call write dec, and then I'm going to move into the AL register a space, and then I'm going to call write char. And that should take care of everything here, right? This is, let me make sure I did this right. Yep. These 3 lines of code is the recursive function call. These 4 lines of code is the cout. And so I can borrow this because that's the same code here, right? For the start of is false. You normally hate duplicating, but sometimes you just gotta do it. And one thing to note here before I finish up, because the only thing I have left to do is this line of code here, is to call this guy, which we will have to do a little work on. But notice that I don't have any unconditional jumps here, and I need this because if I hit this is true label and I run code, and I keep going, there's nothing to tell me to stop. And to, basically, I don't want to write this because this is supposed to be either do A or do B, but not do both. And I can't do neither. I have to do exactly one of the two, like an XOR function, one or the other, but not both and not neither. I have to do one of them. And if I do this way, I will be doing both because then this will fall through and continue on. So I need an unconditional jump to end now, because that gets me around this if statement and gets me down to here. And if you really wanted to put the end if you really wanted to put another label just so you can see it, you can say end if. And I can do that now, or I can say jump to end if. But again, notice all these extra labels that I'm really not doing anything with. The is true isn't being used other than a comment. This end if isn't being used other than a comment. It's a programmer's comment, right? But that should take care of everything up here and basically this line of code here. So the last thing I need to be able to get done is this line of code here. So a thing to note here is I'm going to be calling the recursive function, and I'm going to be sending this value in. But again, notice like we talked about earlier, I am not modifying +8 in any way. I am taking the value, I'm dividing it by 2. That's what this is doing, right? Right shift by 1 is the same as in binary dividing by 2. So I'm going integer division. So if it's an odd number, I'll be turning it even. But then even then, I'll be subtracting 1 and turning, an even number into, because I get an even number or an odd number, and I subtract 1. So anyway, but it's a temporary, right? So I'm going to be shifting this over, subtracting 1, and then pushing that thing on the stack. And because it's a temporary, and I'm not modifying +8, and what are you going to do? Going to divide it by 2 and then multiply it by 2 later? No, it's because if you kill a 1 bit, if you turn an odd number into an even number, you've lost a digit, and you're never going to get it right when you push back. And I'm just rambling on and on about this, but that's not the right way to do things. Is I'm going to use the EAX register. I'm going to move into the EAX register my D word pointer EBB +8. I'm going to take that and I'm going to shift right EAX by 1, so I can divide, so I don't have to do a division by 2. I'm going to do a dec of EAX. I'm going to push it on the stack, and then I'm going to call my function, call R. And when this completes, I don't need to jump to end if because it goes to end if immediately, and then it falls through. And if I did this all right, I'm done. Let me see what happens. An error? I have an error. Let's see. What do I have? What is my mistake? Do you guys see it already before I end if? It must mean that end if is a keyword. That's what I'm thinking. So let me just end if. Put an extra F in here, and let's see what happens now. Yep, that fixes everything, right? So it's hard because C is a keyword in assembly language, DD is a keyword, and apparently end if is a keyword. And so you just got to watch out sometimes, because I wish it would say like you're using a keyword, Wouldn't that be nice? But this tool was built so long ago, and it does what it does, right? So, okay, let's see what happens. Cross your fingers. It will run. It will assemble and run. This is what I get when I run my program. I get 11, 11, 553, blah, 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 this. Let me run this over here and see what I get. And look at that. 553. And you're like, well, are you just running the same thing twice? Let me make sure I'm not, right? Let me just put a C out here and put C++, and then run this again. And we'll run these both 2 times. So I'll run this guy here. This is the assembly language version. That's what I get. And this is now the C++ version. What I get. And now you see, yep, it looks like I have the correct answers. It looks like I'm doing. I would do more testing, but I'm fairly confident that I have everything I need to do to get this job done. So let me bring this back up, make this more visible for you guys. How much code did I write? Oh boy, quite a bit there. And so now, there you go. Here's everything. Get out your microscope, get out your magnifying glass, get out whatever you need. That's everything. Oh, I should probably add more comments in here, but such is life. And so now this is pretty much 100%. It's actually 97% done, or 90. So now this is working for me. And so now that I know this is working for me, the final step before I can put my seal of approval on it is to go through and go, what registers were blown out? Let me just, because this is a void function, and basically, since I'm not returning EAX, any register that I modified inside of here needs a push and a pop. Let me just, so like the push would go here, put a comment so you can see that, and the pop would go here right before all the other pops. And remember, you have to push and pop in reverse order. And so let's go through our code and just go, okay, again, EBP is taken care of for us, ESP is taken care of for us. It's just the other 6 registers, EAX, EBX, ECX, EDX, ESI, and EDI that we have to worry about and go through. And so, okay, let's see, blah, 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 nothing, memory, nope, memory, nope, memory, nope. Here we go. I am modifying EAX. So I do need a push EAX, and I need a pop EAX. If I had a return statement, if I was returning something, then I wouldn't need this. But because I'm returning a void and returning nothing, it's one of the gang, and I return back. Let's see, EAX, AL, it's part of EAX, so you don't have to worry about pushing. You couldn't even push AL even if you wanted to. You cannot push 8-bit quantities onto the stack. You can use 16, but I try to avoid using that, especially with you guys, since why complicate? Sometimes push 16, sometimes push 32. Nope, let's just push 32 all the time. And since we're working in a 32-bit environment anyway, it's more efficient for the CPU and more efficient for your computer to run it anyway. So let's continue on. Nope, nope, EAX already done, AL already done, EAX, EAX, EAX. Okay. Oops. And now you might get confused here. You're like, what? I have a push EAX? Yes, that's the parameter. But everything works out. As long as you put everything and you follow the same pattern, if you've seen my other video, especially the one where I do 5 review problems, you follow the same procedure, the algorithm, right? What is computer science? What is programming? But algorithms. If you follow the same algorithm every single time, you'll never make a mistake when it comes to getting all the pushes and the pops and everything set up properly. If you do everything, I always do this first, I always do this next, and then the thing I always do last is do the final pushes and pops. You never want to be doing this as you go, because you're just going to confuse the heck out of yourself, and you want to finish up on, do the job. But again, remember, if you're using like a div or a mul, if you're using a loop instruction, these things don't generally scream out, hey, I'm modifying ECX, I'm modifying EDX. You have to pay attention. There's none of that here. But you do have to pay attention to that when you go through this. Another thing you can do is just put like a call dump regs right before you call the function and do a call dump regs right after and see how many of the 6 registers have been modified. And then you can go ahead and add the pushes and pops. There's 2 or 3 different ways to do this. I just want you to understand that. But this gets the job done now. And so if I do call this, if I do, let's see, if I do this and I say call dump regs right before, and I do a call dump regs right after, and I run this another time, you will see it does all the work, it prints out all the values, but you will see, again, remember, EBP and ESP don't count, even though EBP was not modified, ESP was. See that? But the other 6 are what I care about. Not modified, not modified, not modified, not modified, nope, and nope. So a void function did not modify any of these other 6. I'm good to go. If I did something like this, I do a move EBX, 4, and I run this again. What do I see here? I see that EBX has been modified, which is not supposed to happen. So that means I would need to put a push EBX here and a pop EBX there if I'm using the EBX register. So again, your contract is you blow out as few registers as you have to get your job done. Put back that workspace as cleanly as possible every time. And then, especially when, like with this, functions are calling functions, which are calling functions, even though it's itself over and over and over again, it all turns out right because you followed a procedure, you followed an algorithm. All right, so that covers everything I wanted to cover in this video. If you have any questions, you have any concerns, did I say something wrong, whatever it is, please comment below, email me at swardb@cod.edu, and I'll get back to you as soon as I can. So we're almost done with the course. Just a few more, couple days, in this case 8 more days to the end of the spring 2021 term, and summer is coming, the end of the term is here. Take a break, you've earned it. Thanks for sticking it out with me as always. Have a great day, everybody. We'll see you next time.